Hi, this is Guillermo Campitelli, and in this video I'm going to talk about probability distributions, and I'm going to explain them using the drone delivery metaphor. Now, in previous videos we made an assumption when we used the drone delivery metaphor, and that assumption was that the size of the region that we were considering, the population is proportional to the size. So now we don't need to make that assumption, so we relax that assumption, and we are actually going to specify the population in each region rather than assuming that is proportional to the size of that region. So size won't matter anymore. What matters is the population. Okay, so in distributions there are three things that we are going to look at: the values of the distributions, the shape of the distributions, and the procedure. And we are going to start with discrete distributions. In other videos we are going to see continuous distributions. Okay, so let's start with the Bernoulli distribution. The values in the Bernoulli distribution are failure and success, or we can call it 0 and 1. And the shape of the distribution is not the unique characteristic of the distribution, because it varies. Sometimes it has a shape and other times have a different type of shape. The procedure is quite simple. And basically we need to use this formula, and the most important aspect of this formula is the value pi, and that value pi in this case is 0.5. And the values x is 1 if success, 0 if failure, so success and failure can be called 1 and 0. Okay, so basically in this city, 50% of the population lives in the failure region and 50% of the population lives in the success region. The way we decide that, how many people live in each area, is given by pi. So if pi is 0.5, then 50% lives in failure, 50% in success. If pi is 0.8, then 80% of the population lives in success region and 20% in failure region. Okay, so now basically we need to determine what's the probability that the first drone landing will be in success region. Well, 0.5, that's given by pi. And what's the probability that it's going to be in the failure region? Well, 1 minus pi. And in this case 1 minus 0.5 is also 0.5, so the probability of failure region is also 0.5. Okay, but that, as I said, pi can change, and in this case pi is 0.8. Okay, so using this formula, what's the probability of the first drone landing being in the success region? Well, it's 0.8 because 80% of the population lives in this area of the city. And what's the probability of a failure region? Well, it's 1 minus pi, and 1 minus pi is 0.2, so the probability that the first landing would be observed in the failure region is 0.2. Okay, that's the Bernoulli distribution, and it's going to be an important distribution, and I'm going to show you why in a minute. Okay, the categorical distribution, the most important thing is that the values are categories. That's why it's called categorical. And it's an extension of the Bernoulli distribution, in the sense that in the Bernoulli distribution had only one pi value, 0.8 let's say, and the probability of landing on the other area, on the other region, was 1 minus pi. In this case we've got one pi per each region, So basically it's like a Bernoulli distribution but with more than two categories. The Bernoulli distribution, there are two regions or two categories, 0 and 1. Here we've got 4, and the way the population was distributed is equally among the regions, and that's because we decided that pi for region pi A or pi 1 is 0.25, pi B is 0.25, pi C is 0.25. Actually, we need we don't need the 4 pi's, we need one less than the number of categories, because once we determine the other 3 pi's, then the other pi will be 1 minus the value of the other 3 pi's. Okay, so simply, what's the probability that the first drone landing would be in region A? Well, 0.25, because 25% of the population lives in that area, and the same for the other areas as well. Okay, so that's the categorical distribution. Now, the binomial distribution is one of the most important distributions that we psychologists use in research, and it is an extension of the Bernoulli, but in a different sense as the categorical. So in the binomial distribution, the values are discrete numbers, so 0, 1, 2, 3, it could be more. So from 0 to whatever number of trials, Bernoulli trials we are going to use, and I'm going to explain that in a minute. The shape is not the main characteristic of the distribution because it varies according to the pi value. The procedure is the most important aspect of this, and the procedure is quite interesting because it starts with a Bernoulli and it's constructed and it finishes as a binomial. Okay, so this is the procedure to construct a binomial distribution. We start with the Bernoulli. Let's say the pi of the Bernoulli is 0.8. Now, until now we've been considering just one drone landing. So we said, what's the probability that the drone would land in one region? Now we may consider more than one drone landings. So in this case, we are going to consider 3 drone landings. Is what we say in statisticians called Bernoulli trials. We are going to do 3 Bernoulli trials. Okay, so these 3, when we consider more than one drone landing, we get one aspect that we didn't have before. So we can consider not only what's the probability that the drone would land in an area in that landing, but we can consider, let's say, 2 landings. So what's the probability that we are going to observe 2 drone landings in that area? What's the probability that we are going to observe 1 drone landing in that area? And what's the probability that we are going to observe 0 drone landings in that area? So it's not just whether the drone will land in a specific area, but how many drone landings we will observe in that area. So that's something that we haven't seen so far, and with the binomial distribution it's we can do that. Okay, so basically if we are going to observe 3 drone landings, we want to know what's the probability of observing 0 drone landings in the success region, 1 drone landing in the success region, 2 drone landings in the success region, or 3 drone landings in the success region of this city. So in order to do that, we create a new city based on repeating drone landings in the binomial city, in the Bernoulli city. Okay, so basically we concentrate on the success region and we ignore the failure region. So, if the probability of the first drone landing in the success region is 0.8, we want to know what's the probability that the 3 drone landings will be in the success region. Okay, we can see that in this city. The way we calculate it is like this. What's the probability of the first drone landing being in the success region? 0.8. What's the probability that the second drone landing will be in the success region? Is the same, 0.8. And what's the probability that the third drone landing will be in the success region? Same, 0.8. So what's the probability that we are going to observe 3 drone landings in the success region? Well, we use the product rule of probability theory, 0.8 times 0.8 times 0.8, and that's 0.512. Okay? Now, what's the probability that we are going to observe 0 drone landings in the success region, or the number 1 region in the Bernoulli city? Well, we know that the probability of not landing in the success region is 1 minus 0.8, that is 0.2. So the probability of the first drone not landing in the success region is 0.2, same for the same drone landing, and same for the third drone landing. So again, we apply the product rule, and we got 0.2 times 0.2 times 0.2, and that's 0.008. So the probability of observing 0 drone landings in the success region when we use 3 Bernoulli trials or 3 drone landings is very, very small, 0.008. Now, these are easy. Now, we can also ask, what's the probability of observing 1 drone landing in the success region, and what's the probability of 2 drone landings in the success region? And this is a bit more complicated. Okay, let's say that we want to determine what's the probability of 1 drone landing in the success region of the Bernoulli city. So we need to do 0.2 times 0.2 times 0.8 because these are probabilities of not landing in the success region, and this is probability of landing in the success region. So we've got 1 successful landing. This is the probability for 1 successful landings and 2 non-successful or failure landings. But then we have to multiply by 3. Why we multiply by 3? Well, because it could land in the success region in the first trial, in the second trial, or in the third trial. So we've got three possibilities in which we are going to observe only 1 landing in the success region. Either that landing was in the first trial, in the second trial, or in the third trial. And similar is for observing 2 drone landings. So we've got 1 is unsuccessful, so the probability is 0.2, and 2 successful ones, so their probabilities are 0.8. Now there are 3 cases in which this could occur. So the unsuccessful landing could be in the first trial or the first landing, in the second or in the third. So that's why we multiply this by 3. And the values of these multiplications are the ones shown here. So basically we started with the Bernoulli distribution, and we now have a completely new city, which is the binomial city, with a pi that comes from the Bernoulli, 0.8, and it tells us the probability of of observing successful drone landings. Now, we've got now a new distribution on its own, and we now concentrate on this distribution only. And so we say, in this city, what's the probability that the first drone landing is in region 0? Okay, very small, because the population in this region is very, very small. What's the probability? So it's less than 1%. What's the probability that the landing is in region 1? Well, almost 10%, 0.096. What's the probability of observing a region landing in region 2? Well, 38.4% or 0.384. What's the probability of the drone landing being in region 3? Well, a bit more than half, 0.512. Okay, so this is the last discrete distribution, and the important thing again is to take into account the values, the shape and the procedure, and to see what is important in each probability distribution, what aspect is most important or more characteristic. In the binomial, the procedure is very, very important.